a round of applause for those who discovered us for this month. That's exciting. Well, you're in for a good treat. We have two excellent speakers today, both alum from the University of Texas at San Antonio. Yeah, couple fans? All right, cool. Okay, great. So I'm Tracy Becker, one of your hosts, and we have
Christine Ray.
Woo! Michael Velez.
And
I'm back.
Brian Beck over here on. And Aaron is in the back. He's going to help us out tonight, too. Yeah, so we can go ahead and go to the next slide.
Okay. So what is Astronomy on Tap? Astronomy on Tap isn't just us in this room right now. It's actually a worldwide event. I forget where it started, but it has locations all over the world now, a lot in the U.S., but we're, spreading out across all of the continents. So everywhere people get together once a month and talk about astronomy at some brewery and have a lot of fun. And I think that's the Astronomy on Tap, right? Okay. That would have been helpful earlier, huh? Okay, what did I say? Monthly event. It is a monthly event in San Antonio also. You can follow us there if you want to keep up with our future events, especially if this is your first time and you just enjoy it so much, you can't stay away. World-class scientists, we got that. Interesting, yes, that also. You can win prizes. We will have trivia and prizes at the end of this. We got some extra special prizes, in fact, actually, because I was cleaning out my apartment and found a bunch of cool space stuff to give away to all of you. So you have that to look forward to. Okay, and that is Astronomy on Tap.
Very good. Tag in front of that. And then this QR code sends you there, probably. I don't know.
To our website.
And then if you have a question at all, you can feel free to text for the speaker so that we can ask afterward, 5620. Yes, I'm prepared to get blasted with messages. And now, without further ado, we can get started on our program.
Okay, so how many of you here MASPEXs that live in Texas? All right. Okay, great. So introduce to present Dr. Christine Ray, who has been an organizer with us for many years now. So we're sad to see not only is this the finale, her giving her presentation, but also it's her last day here as an organizer and in San Antonio. So everybody, before she even gets started, let's hear it for her. Going on to her next. So Dr. Christine Ray just finished a mini postdoc at the Southwest Research Institute, where she worked on the Europa Clipper mass spectrometer team. She's also an alumni of the UTSA SWERI PhD program. Where she wrote her dissertation on the habitability of ocean worlds. In just a few days, she will be hanging her hat in Tennessee on the drive from Texas to Washington, D.C., where she will be starting a new science policy fellowship. But despite this, she will always love Europa and hopes to one day see a Europa lander dig beneath the ice and find all of the ice. And her what we do is when she says the drinking word, you're gonna raise your glasses, say woo, and take a sip. And her drinking word is
life.
Just a reminder, drive safely, carefully, responsibly. We are not responsible for you getting home safely, so please make sure you do so yourselves. All right, and with that, I'll hand this over to Christine.
Thanks. Okay. Do I need to be here? I guess I do. This is a bad angle, but you know what? It's all right. Like here. Okay. All right. Hi, guys. I, as Tracy just introduced, am Christine Ray, and I'm going to be talking to you about the Europa Clipper mission. and particularly the role that Texas will be playing in the Europa Clipper mission. And I hope you all enjoy it as much as I do. Okay, is this going to work? Oh, maybe it's this way. It's that way. Okay. Except I jumped ahead. Okay, so before I dive into Europa Clipper, we've kind of hinted one of the exciting things about ocean worlds about Europa Clipper is the life aspect. Excellent. So I kind of want to talk to you about how we're doing that. How do we look for life in the universe? Well, oh gosh, this may have, hello? Okay. Pause on the life. One person got it. Orbiting Jupiter, but it's in what we call an orbital resonance with Europa. So these two things are orbiting in such a way that Ganymede is also constantly pulling on Europa, and these things are, they're little worlds that have oceans on them. But the cool thing about these is, unlike Earth, where you just have water somewhere, these have a global subsurface liquid water ocean, so the entire thing is covered in ocean. So this is Europa as an example. It's got a lot of rock. It's large enough. We think it also has a metallic core. And images on top of that. See the entire planet. Again, ice. Okay, so now that we know ocean worlds can exist, we know they're a thing. Again, if we're taking this follow the water approach to looking for life, then we now have the Goldilocks zone still. That's all good. But now we've opened up the rest of the outer solar system into places where life could potentially exist. And it turns out we have a lot of these, but all of these things across the outer solar system we think could have abundant liquid water on them. So it's really cool too, because Earth, like, that's a fairly large planet as far as the rocky planets go. It's got 1.3, I believe the Z stands for zeta liters of water on it. And then we look at like the Jupiter system, for instance, and we have Europa, Callisto, Ganymede. These things have, we actually think, again, looking at Europa, that Europa has these plumes, which is very exciting. So we've looked at Europa with the Hubble Space Telescope a few times. They found what they think is evidence for plumes just by looking for hydrogen and oxygen in certain abundances that indicate water is condensed there. The Galileo magnetometer team, after these observations came out, looked back at their data and said, oh yeah, there could be plumes there too, stating that there may be plumes in Europa. And that's great for us because it means we can fly a spacecraft right through the plume and sample the ocean that way, instead of having to land on the surface and drill through 10 kilometers of ice to get there. So Europa, good candidate, has an ocean, potentially has plumes that we can sample very easily. This is all good news. So why don't we just go there and land some people on Europa and look for the ice squids? And that's actually, I wanted to give a shout out to this movie called Europa Report. Has anybody seen this movie? Okay, a few of you. I highly recommend it. I didn't know Europa was a thing until I watched this. It was like, I cannot believe that's a real place, and then found out there was a whole mission going there. Spoiler alert, so they send some humans to Europa. They're doing much like what people here are doing. We're looking for microbes, we're looking for what's going on at the ice shell, stuff like that. But then they all get eaten by ice squids at the end, which is very exciting. And as much as I, and maybe others in this room, would love to go and get eaten by an ice squid in Europa myself, it turns out that NASA has a more kind of conservative process for sussing out ocean worlds for life before we're going to be allowed to do that. And that is the Europa Multiple Flyby Mission, otherwise known as Europa Clipper. So this thing right here is going to be launching in October of 2024. It is a targeted mission to Europa, so that's the first time we've had a mission going to suss out an ocean world specifically. We've obviously investigated other ocean worlds and other missions, but those have gone to things like Saturn and just accidentally found ocean worlds in the process. This time we're like, we know Europa's cool, let's send a mission to that and that alone. And it's going to pass over Europa 45 times, which is a lot more than we've ever done before, and do lots of interesting things. Science investigations or instruments. This is a very big, expensive mission, and we're going to do lots of really, really cool stuff, and I wish I could talk about them all, but I only have so much time here. So I want to highlight these three here, because those are all coming from right here in Texas. So 3 out of the 9 science investigations, Texas is building like 30% of the science on Europa Clipper, which I think George Strait himself would be very approving of. Okay, so the first is reason. So this is the radar for Europa Assessment and Sounding Ocean to Near Surface. So that is pretty exciting. Let's give a round of applause to them. Good job, UVS. Okay, so ultraviolet spectrograph. What does that mean? Well, it means it measures light in the ultraviolet wavelength. So unlike when you take a photo with your camera, what you and I are seeing here, that's all in the visible wavelength. The ultraviolet wavelength is more high energy than that. So it's things you can't see with the naked eye. But it's really important to look at those wavelengths because that can tell you what's floating around in the atmosphere. So this instrument is essentially going to look at what kinds of chemical species are in the atmosphere in the plumes. And the extra exciting thing is that that is actually to confirm that they're there. Because again, if you can find that hydrogen and oxygen in the right abundances condensed together and say, okay, to do operations up here when we're no longer close to Europa, that's great. It means we have a little bit more horsepower available to us. The other cool thing about the cryotrap is that we can search for abundances. Like what, you might say? Well, we're looking at all of these things. This is basically a summary of what I worked on as a postdoc for all of these things with MASPEX. So at the surface, and during that original flyby, you might just get some of the most abundant species, but then based on what those things trace, we can look for things present in much, much, much smaller abundances and get the complete picture with this cryotrap. So what does that include? Well, volatiles and organics, so gaseous species and organic compounds, things with carbon, hydrogen, oxygen, things that make up, I bet you thought I was done, the building blocks of life. And then, so I mean, those are like good for life already, right? But they're also produced by these hydrothermal systems I mentioned, these things where we think life may have originated in the first place. So by looking for these things, we can figure out what's happening in the interior, if these hydrothermal systems are present, if we have the ingredients needed for the Chinops elements for life. And we can also look for life itself in mass specs. So one of the things our team is working on is putting them through a mass spectrometer and looking at what the chemical signature of those microbes is, so that we can go to Europa armed with that information and say, okay, we might not have found this in the initial flyby sample, but we can look for those things in our cryotrap sample that are probably present in very, very low abundances and figure out if there's microbes there, figure out if there is life coming out of Europa. And I think that's pretty cool. And all in all, if there's just one thing I want to leave you with today, maybe details of all the instruments aside, and again, that was just 30% of them, the 30% coming from Texas. There's a lot more, and they're going to do equally cool things. It's that Europa Clipper, as Michael Velez told us over, is pretty cool with this, with all the instruments on here, is absolutely state-of-the-art, combining mind-blowing. So again, launching in 2024, I think we're going to get there around the 2030s, hopefully get data back shortly thereafter. So hang out for another like 10-ish years and maybe habitable, and whether there is life there itself. And that is all Mulder has for you and all I have for you. Thank you for listening.
Round of applause again. I think it was a very good Europa discussion. All right, so we got some. Is there anything? Be brave. Yes. I got one.
Is there really enough mass in the outer planets like Pluto or planets like that to create tidal forces that are enough to create liquid, whatever, moons? You know, I mean, it seems like there's sort of a threshold for that, and some sort of mass, like Saturn mass.
Yeah, I have no idea why we think Pluto's an ocean world, to be honest, because I don't know. I mean, it is part of the Kuiper belt, right? So maybe if you have other Kuiper belt objects tugging on it, that's enough to create that differential pull. But yeah, it's definitely an outlier, and everything else is a moon orbiting a gas giant, and that one's not. So, excellent question. Answer, Sam? Well, we kind of are. JUICE is kind of doing that. JUICE and Ganymede and Callisto is a target, right? But I think it's primarily Ganymede. So I think we were just like, we'll let Europe do that, and we'll do this, and then we'll collaborate, and then we get them both. And I think also we know a little bit more about, like the first time we even were like, hey, crashing into Ganymede, right? Yeah. which is cool because I also have been told like the MASPEX team, especially. I think there's a lot of different teams in Europa Clipper that actually have their own simulations and models. Because we also forward modeling is really important for this stuff. So being able to say exactly what we think Europa's atmosphere is going to look like in different density distributions and stuff like that, to be able to decide what we want to prioritize first. And then that also saves us some work because we already have the model, and then when we get there and find out this isn't true at all, then we can just tweak it a little bit, add some updates, plug in the new numbers, and say, okay, now this is saying this would be a really interesting spot to look there. So it's kind of a living model span, and hopefully after the mission life.
Very good. Is that in the room? Because I like this question. What advice would you give a teenager who is interested in space study?
Take a lot of physics and math and programming as early time. So definitely take those classes, get involved in research as early as you can, even if meant for these smaller, what are they called, teaching schools where people don't have access to research necessarily. Shoot your shot, apply to those, and for sure, just keep trying. I mean, most things, it sounds cheesy, but like, you know, if you just don't give up and just apply to everything, don't get imposter syndrome. Don't ever tell yourself like, oh, they're not going to take me, I'm not good enough, because I, you know, shot myself in the foot one too many times doing that. Just be like, do it, shoot your shot. Well, Python would be helpful because at least just learning how coding works, you can learn a new language more easily than just learning how to code in the first place. So that's what I got for you.
Very good, thank you. Let's thank our speaker once again. Be sure to order more drinks and food as needed, and we'll see you soon.
As long as we just connect to that same feed, we should be okay. It might be a combination of use of that PowerPoint. I don't know if one of these sites was set up with Chrome, right? Okay, that's the Chrome one, because that's y'all's main one for the Chrome. And then that switched over to the PowerPoint? All of the other ones are in PowerPoint. Okay, so we're sharing one of the screens, but not the other, apparently. At least, yeah, and then when we did, maybe we're only sharing the screen, whatever screen that is, and then the PowerPoint, then it messes up when you do the HUD, because to get me over here. Okay, now it's funny, it just changed. Oh, it did just did. Okay, I'll say that too. We're dropping crazy amount of frames on this network. This internet is horrible. This whole setup is horrible. I do really good productions if I have the good equipment, but this is nuts. Yeah. It is. I mean, to have the video back there and the audio up here, this is not ideal at all. We're trying to make do, but I don't know. Adam, he texted me. He said for the 2 seconds he was able to get on this stream, he could hear it. It sounded okay. To me, it was kind of low, but in the room it sounded fine. So I didn't want to mess with things. So anyway, we're good. We're running with it. I'm recording it. So. Okay. Right, yeah. But then one feed goes there, whatever that one is, that's a screen we need to grab, or that's a screen we need to share. I'm gonna put my laptop up here so we can see from back there. I'm gonna go use the rest. Yeah, go for it.
All righty, everyone. Let's start to get settled in. Maybe about 30 seconds, you know, we'll give a generous person. It's good. I like their style. What were you talking about?
Which microphone should I use, sir?
Okay, everyone. Let's settle back in. Second half of our program tonight. We will start with our monthly segment, Astronomy News, Astronomy in the News, and as usual, Caleb Gemar, student in the UTSA SWIRI program, will give the news, and let's give him a round of applause.
All right, so hello, and so we'll go ahead and get started with this month's section of Astronomy News. A fair number of things to run down here. So let's see, first of all, the September skies. So this is what the evening sky will look like around 10 o'clock p.m., about mid-month. Again, we do have this wonderful Milky Way overhead. If you are out in a nice dark sky, please do observe that with binoculars. If you are under a very dark sky, an awful lot to see there. Cannot stress that enough. But Jupiter steals the show this month. So in this image here, you see it rising over in the east. Wait until about 1 o'clock in the morning. At 1 o'clock in the morning, later in the month, around September 26th, it's going to be almost right in front of you in the south, there in the sky, and it will be at opposition, meaning that we will actually be extremely close to Jupiter at that time, and it will be very, very bright. If you're observing it with a telescope, you will get a very nice view of that planet. Through a telescope, generally, you are able to see the 4 largest moons orbiting around the planet, Ganymede, Callisto, Io, and Europa, what we tend to call the Galilean moons, so you do not want to miss that. Also, do not miss Saturn if you have a telescope. It is generally over the south during much of the month right there. So, again, never want to miss the ringed wonder. And yes, you can see the rings through a backyard telescope. Now, the big news for this month is an upcoming impact of a spacecraft with an asteroid, actually a moon of an asteroid. The DART mission will actually be conducting this impact experiment on the moon of the asteroid Didymus. That moon is named, someone remind me, I'm sorry. Dimorphos, thank you, yes. That moon is Dimorphos, and that will be happening on September 26th. In the lead up, though, the imager on board the DART spacecraft actually has a very slight view of the asteroid system itself, Didymos, right there. Earlier, just a little over a month ago, the announcement was made that another mission that is going on right now, the Lucy mission, actually has one more target added to its slate of asteroids to visit. So this mission was originally scheduled to visit 7 asteroids, but in the intervening time, they found out that a couple of these asteroids have moons as well. So that count has went up to 9 for the Lucy mission. The asteroid Polymel has a very small companion as well. So when the Lucy mission reaches that asteroid, they will be able to get an examination not only of the primary asteroid, Polymel, but also its companion asteroid. So this was a rather interesting discovery that was just announced today. Data from the Very Long Baseline Array. This is a group of a number of radio telescopes that are spread over a wide swath of the United States. Has been used to produce a very detailed orbital map of a binary star system with an exoplanet within it. So in this rendering here, you see the larger orbit of one of the members of the binary star system, and then the larger member of the system right there, and then the planet orbits within. This is the first time that any such detailed imagery has, or sorry, not imagery, any such detailed orbital information has been produced for such a system. In case you want to know, that is the binary star system with planet GJ896AB. How many of you are going to remember that name tomorrow? Didn't think so. All right. So again, very, very fascinating discovery using radio astronomy information. James Webb Space Telescope keeps producing some really great preliminary information, and it will be very fascinating to see what comes even farther down the road from that space telescope. So one of the announcements that was made just a little bit ago was that there actually is a exoplanet that has been directly imaged by James Webb Space Telescope. This is somewhat preliminary, but nonetheless, observing this star, HIP 65426, James Webb was able to use the various instrumentation to observe this exoplanet. So the main star that orbits around has been blocked here, and then you have the exoplanet itself appearing as the blobs in these different wavelength images. And if you did not see just a couple days ago, this really beautiful image was revealed from Webb, this one of the Tarantula Nebula. And I cannot stress enough, please go online, download the full resolution version of this picture, zoom in on it, you will not be disappointed. There are so many little details here that are not apparent in this lower resolution copy that I've used in this presentation here. So definitely find some time to take a look at that. Really, really fascinating stuff. Come on. There we go. So, do not miss, again, I always say this, the solar eclipse is coming up. In 2023, we have an annular eclipse coming up. That's just next year. And so in that annular eclipse, if you have some of those nice solar eclipse glasses, you can take a look at the disk of the sun and you'll see this shadow of the moon passing in fracture. It's not really a shadow, it's the silhouette, I should say, of the moon passing in front of the sun. And then, of course, in 2024, a total solar eclipse where if you're in the line of totality without the glasses on for a brief moment of time, you'll be able to look up and see the moon blocking the sun completely and the outer atmosphere, the corona of the sun in very great detail. So you do not want to miss that. Eventually, SLS will launch. I know this was supposed to happen a little bit ago. It didn't happen last week as we all hoped it would, but it will happen. If you could wait for James Webb, you can wait for SLS, okay? So just keep watching out for that. Very eager to see that rocket launch take place. And with that, that concludes Astronomy News. Thank you very much.
All right, thank you, Caleb. Thank you. Let's see, I think, I don't know if we're going straight into, let's see. Yes, we are. All right, Christine.
Okay. I would like to, this is on, right? Okay. I am happy to introduce our next speaker, Dr. Michael Starkey, also a UTSA SWRI alum. So Michael just completed a Bachelor's of Science in Mathematics at no, that was a while ago. Completed a Bachelor's of Science in Mathematics at UT Austin. He then joined the UTSA SWERI Graduate Research Program and obtained a PhD in physics in May of 2021. So congrats on that accomplishment, which was recent. As a graduate student, he used data from the Magnetospheric Multiscale, or MMS, mission constellation to investigate particle acceleration at collisionless shock waves in space. That sounds very complicated. He also assisted in the calibration of the Superthermal Ion Sensor, or SIS, which will fly on the CUSP mission. Michael started his postdoc at SWERI in July of 2021, where he performs research using data from the Interstellar Boundary Explorer, or IBEX, and Parker Solar Probe, PSP, spacecrafts. His research interests include the interaction of the solar wind with Earth's magnetosphere and solar energetic particles in interplanetary space. What is your drinking word going to be? Okay, well, TBD then. Let's give it up for our speaker.
Thank you, thank you. Yeah, and I want to note that that instrument, the SIS, is supposed to be launched on the Artemis 1, and it wasn't, so waiting for that, very excited. All right, yeah, thank you for having me. Thanks for the introduction. And so today I wanted to talk about the interaction of the solar wind with Earth. The interaction of the solar wind with Earth's magnetosphere, or its magnetic field. And in particular, I'm going to talk about a fundamental process that occurs there called magnetic reconnection, hence the title here. So we'll get to that. But first things first, the drinking word. All right, so today I chose plasma. Yeah, get ready to drink. So plasma is an ionized gas an ionized gas consisting of positive ions and free electrons, and it's a fourth state of matter. So, So if you start with a solid here, that's really referring to a collection of atoms that are rigidly held together. They're not really free to move independently of each other. As you start adding heat, these atoms or molecules begin to have a little bit more freedom. They can move a little bit more, and that's what we call a liquid. You keep adding heat, these atoms, molecules, they'll eventually get to the point where they have enough energy to move kind of freely of each other and independently. And so that's a gas, like the stuff we're breathing right now. Now, something really cool happens once you keep adding heat. The actual atoms themselves start to break apart, and electrons have enough energy to be free from that bound state. So when that happens, you get a collection of positively charged ions and electrons that are just flying around each other and can move basically independently of each other. Now, the one similarity between solid, liquid, and gas is that typically these atoms, molecules making up these states of matter are not charged. They're neutral. But so with a plasma, it's different. You have charged particles moving around each other. And so what this means is that when you have an external magnetic field or electric field, these charged particles are going to feel that, and they're going to react to that force. What makes it even more complex is that Maxwell's equations tell us that moving charges will generate electromagnetic fields. So in this plasma, these particles it's a really complex and dynamic interaction where they're reacting to external fields, generating their own fields, and makes it a really fun mess to try to describe mathematically. So that's a whole topic in space physics, is plasma dynamics. So now, contrary to what a lot of people think, space is not empty. It's full of plasma. And that's, again, part of the stuff that I study. So again, the talk today, I wanted to describe how the solar wind, I'll get to that, how the solar wind interacts with Earth here. So it starts with the sun. The sun's a big ball of plasma that is constantly undergoing fusion at its core. There's a lot of other processes going on that result in it constantly emitting UV light and the visible light that we see today. In addition to that, it's constantly emitting this highly charged, high energy flow of particles, ions and electrons. And so this is what we call the solar wind. It's this constant flow of charged particles that are being emitted from the sun and basically in all directions. So as this plasma or solar wind expands from the sun, it fills the heliosphere and it'll interact with different bodies in the solar system, such as Earth. So you might think, you know, this really high energy charged particles coming at us sounds kind of dangerous. It is, but luckily we have a nice magnetic field here that protects us and acts as a shield, shields us from these particles here. So that's the initial step in this interaction. Once these particles cross this, what we call a bow shock, which is analogous to, think of a large rock in a river. You get a wave standing in front of that. And that wave is really deflecting and decelerating those water particles around the rock. And so that's the kind of the analogy here for what we call this bow shock, which is a magnetic collisionless shock wave in space, which we don't have time for that. So anyways, this as the solar wind comes in through the bow shock, it reaches this point where it kind of comes to a standstill. This is where the solar wind pressure balances with the magnetic pressure from the Earth's magnetic field here. And this is what we call the magnetopause. At that point, something really cool happens, which is magnetic reconnection. And this is a fundamental process that basically converts magnetic energy into kinetic energy. And this is a process that happens all over the universe at supernova shocks, in the coronas of different star systems, our sun for one, and also at planetary systems here, or at planets here. And so what this does, we'll get into it in more detail in a bit, but it basically allows plasma to be convected up and over the poles of the Earth and into the magnetotail here. And then once in the tail, you can get another bout of reconnection, which sends plasma earthward and tailward, and that can result in things like the auroras or substorms, which can disrupt technologies here on Earth or in space too. So the point of this is just to kind of show that, or describe the real general process by which solar wind plasma can enter into the magnetosphere and how it circulates throughout the whole global magnetosphere. So this, I believe, yeah, this is just a little movie showing, depicting solar wind particles coming in, interacting with this, not really the bow shock, but we'll call it that for now. And you can see they're just deflected, decelerated, and move around the Earth. Now, zooming in on the poles here, and this is how auroras, one way that auroras are generated, but we can't really talk about that for the time's sake here, but it's just a pretty picture there. But one thing I wanted to say is that an important feature of the solar wind is that it has an embedded magnetic field, which we call the interplanetary magnetic field. So this is the magnetic field that's connected to the sun, and as the solar wind expands from the sun, this field becomes frozen in, and the plasma kind of drags out the field along with it. And this has implications for magnetic reconnection that takes place here at Earth, as we'll see. Okay, so this is a Dungy cycle. This is basically the cycle that describes how plasma circulates throughout the whole magnetosphere. This is a really old schematic. We don't need to, spend too much time on it. It's, but just kind of the idea is that solar wind comes in here from the left. You have the IMF, interplanetary magnetic field, being dragged along. As it encounters Earth's magnetic field here, you can get reconnection, which I promise we'll talk about in just a second. And once that happens, this plasma is actually accelerated up and downward in this image, and can kind of be dragged over the poles here. And you can see, so this magnetic reconnection is resulting in a change of magnetic topology, where the IMF field line is now reconnecting to one of these Earth field lines. And so I'll kind of get into that in a little more detail here. But yeah, I just wanted to show that this is a little more detailed schematic on how this process is taking place. And again, eventually this plasma enters into the tail, and which is what we call the backside of the Earth's magnetosphere here. And once it's there, it can undergo reconnection and be accelerated away from the planet or towards the planet. And again, this can then result in things like the auroras, where particles funnel down the field lines and generate nice, pretty lights. Yeah. All right, so what is reconnection? Sorry. All right, reconnection, yes. It's a physical process that occurs basically all over the universe, and it's where, again, magnetic energy is converted into kinetic energy in the form of heating or acceleration of the local plasma. So as you can see here, this is kind of a really basic schematic of what takes place. These are magnetic field lines, and it's now when you have two populations of plasma where they have oppositely directed magnetic field lines at their interface, eventually you can get enough, if you have the right conditions and you have pressure building up and things, those field lines can snap, kind of. And they not snap, but enough pressure builds up to where they can, it's a violent process that just reorients them in some way. And what happens is you can see this downward facing field line now connects to the upward and vice versa. And when that happens now, these field lines are accelerated away from the reconnection site, and that also, that energy from the magnetic field lines goes into heating of the particles and accelerates them away. So this is a little bit of a nicer schematic, or more realistic. And you can see you have the opposite directed field lines here. You have plasma flowing in from the top and bottom. And once reconnection goes, you get what we call plasma outflows, or plasma jets, or plasma exhausts. And so this is one of the telltale signs of reconnection that we can measure in space. And now you can kind of think about, if you had a spacecraft that's equipped to measure magnetic fields and ion velocities and electron velocities, and then say that spacecraft flew right through one of these reconnection events, well, you could probably paint a picture of what's going on by looking at those observations. So that's exactly what the MMS mission does here. It's a mission that's comprised of 4 identical spacecraft. It was launched with the primary goal of investigating reconnection here at Earth, and it has some really high capability instruments that allows us to do that. And so what we're looking at on the left, so these are figures from a science paper by Jim Birch, who's the SWIRI vice president. And he's, in this paper, he was looking at an actual event in which MMS flew right through a reconnection site, right there. So this is a simulation reconstruction of the event. But you can see as the 4 spacecraft are coming up, there's a reconnection that takes place right there. You can see by the field lines that then shoot up and downward. And so this was really kind of a lucky find, and it was a really cool event to look at. And so I just wanted to show this figure here, which is actual observations, to give you an idea of how we diagnose this reconnection with using in situ observations. So what we're looking at is a snapshot where the 4 spacecraft are located right near the reconnection site. And these circle plots are velocity distribution functions of the electrons. So it's basically telling us how many electrons are moving at what velocity. So the distance away from the center represents the velocity. The color says how many particles are moving with that velocity. And we just focus on these 2. Well, look at the green spacecraft here. That's right above the reconnection site. And so what do you expect? Well, we remember there's the ion and electron outflow. So that means that electrons should be moving away from the reconnection site. And if you look in this distribution here, well, that's exactly what we see. We see this kind of crescent feature, and electrons are moving upward away from this reconnection site. And you get a similar thing down here. It's not as well pronounced, but this was just a kind of quick overview and idea of how we can actually look at this reconnection and analyze it using in situ data from different spacecraft. And again, this really allows us to probe the more fundamental meanings and workings of magnetic reconnection. So with that, yeah, I'll just summarize up. It's a little quicker, but so again, Earth's magnetic field protects us from the solar wind. It gives us it shields us from these harmful rays and particles and plasma. And I mean, look what happened to Mars. So we wouldn't be here without Earth. I mean, magnetic field. Anyways, and the solar wind circulates out through the magnetosphere via this Dungy cycle, which is really enabled by magnetic reconnection. And magnetic reconnection, again, is this fundamental process, occurs all over the universe, and it's very interesting to study. And yeah, thank you. Go plasma. Oh yeah, there's some auroras. So. We can trade. Hello?
It would help if I turn it on. They don't teach this stuff in magnetosphere class.
Blame Steven.
A very, let's think again, Dr. Starkey. Very cool topic. I remember when I first learned about magnetic reconnection, it sounded like something an evil scientist would do, reforming magnetic lines.
It doesn't make too much sense, but.
That's like, ooh. All right, we do have some questions before, we get the number up. So a general one, what is, if any, the difference between magnetism, electromagnetism, and gravity? That's the question.
So, I mean, electromagnetism and gravity are fundamental forces. There's 4 fundamental forces. There's the strong force, weak force, basically E&M, electromagnetic force, and gravity. So the difference between it would be, I mean, I don't know how deep to go into this, but so electromagnetism is basically driven by charged particles, electrons and protons. And you have this attraction, protons will repel them, and electrons and protons will attract to each other. Gravity is driven by like the Higgs boson particle, which I don't know too much about. But yeah, basically it's anything with mass will have an attractive force towards it. So it doesn't see charge or anything like that, but it's a force that just depends on mass. And yeah, so I hope that answered the question.
Very good. Yeah, I think that's good. Do humans have a plasma field or plasma body?
Well, I don't know. We should measure that. I mean, yeah, I guess.
Bring MMS back.
You rub your arm with a balloon or something. There's some kind of static electricity, electric effect going on there. So I haven't thought about that too much, though.
It is an interesting. What happened to Mars?
Oh, yeah, solar wind took over. No, so Mars didn't have it used to have maybe a magnetic field, but over time the solar wind basically eroded the Martian atmosphere, I think, and so without the atmosphere and it doesn't have an internally generated magnetic field. I guess because it maybe cooled down too much. I'm not a planetary expert, but so Earth's magnetic field is generated by its mantle that's basically moving plasma, which generates a magnetic field, and that's why we have this nice dipole magnetic field protecting us. And I don't think, and Mars doesn't have that, so they didn't have this magnetic field protecting them, and over time their atmosphere got eroded away by the solar wind, I think, and so I mean, It's still there. It's still a nice planet, I think, but it just doesn't have humans yet.
That's very. All right. The next one, I think this is a good question too. What has been the coolest discovery by the MMS mission?
Probably electron scale reconnection. Yeah. No, yeah, so I actually don't study reconnection that specifically, but that's the one that I've heard about the most from the MMS mission is electrons. So I guess before MMS, they thought that the reconnection was only, or they didn't know or thought that reconnection was only occurring on ion scales. And that the ions and electrons were always involved. But with MMS, they were able to probe much smaller scales in time and in spatial distances. So they were able to see events in which only the electrons were taking place in the reconnection process, and ions were, I don't know, I guess oblivious to it. And so that was a big deal in the scientific community, yeah. And actually, I think the paper I was showing was, actually, I don't know. I don't want to speak to that. Yeah.
If you're standing at the pole, or either of the poles, are you in danger of being hit by the solar wind?
Probably not. No, so, I mean, yeah, these particles will, I mean, we're getting hit by radiation right now. There's galactic cosmic rays that are coming in, and they penetrate through our atmosphere and the magnetic field. So you're always getting hit by some tiny, dose of some kind of particle. But no, I wouldn't say you should worry about standing at the pole because that interaction with the aurora, the atmosphere stops most of it, pretty much all of it, yeah, so.
That's good.
Yeah.
How does magnetic reconnection vary at other planets, and is it different than what happens here at Earth?
Well, so I mean, we're lucky that we have Earth as kind of a laboratory that we can actually send spacecraft to. Now I know that there's been work at reconnection at Saturn by one of our own grad students, Ryan. But yeah, so I mean, as far as, I mean, it's a fundamental process. So of course there'll be differences in the way it looks at different planets, but you know, for instance, here at Earth, we have what we call, on the day side, for instance, it's asymmetric reconnection, and that means that on one side you have a much higher density of plasma, and on the other side of the reconnection lines, it's much lower, and that, you know, has certain implications for how it looks. And so, yeah, there's different types of reconnection. So, it'll look different at different planets, but the fundamental process remains, I think, the same.
Very good. I think I'll hold this as, we'll take some, from the audience. Yeah.
So plasma is, it's when you add, you take a gas and you just keep adding heat to it. That's one way, I guess. And eventually the electrons in these neutral atoms will have enough energy to break free of their bonds and kind of be moving freely about in tandem with the, what's that? Superpowered liquid light? Yeah, I don't know. What's superpowered liquid light? I'm sorry. Oh, no, yeah. Okay. Oh, like liquid, I get it. Okay, I'm sorry. Yeah. Yeah, I guess that's a good way to put it. I mean, it's just really hot, charged gas that's, flowing around. It's too hot to where the particles don't stick together anymore. So you have electrons literally, they break apart from their helium atom, parent atom, and so now you have a positively charged helium ion and an electron moving around instead of them stuck together moving around together. Yeah, but friction is, I mean, on Earth when we have, it's like air friction, for instance. It's in space the density is so low that you're not going to have particles actually colliding. So, it's a cool thing. I don't know, it's everywhere in space, but it's not, I don't think it's too, here on Earth we have laboratories for it, but I don't think it's very common.
Yeah, with the little I understand about pulsars is that the magnetic field is responsible for accelerating particles that jet out from the pulsars. Is that reconnection, or is that a completely different process altogether?
I'm not totally sure. Yeah, I actually don't know, but it could be. I mean, if anyone else has a comment on that.
Is enough known about the physical laws of the solar wind so you can predict the size or strength of the solar wind from a blue hypergiant or a red dwarf or other types of stars? Or is that to be determined?
Yeah, again, I wouldn't be. I haven't looked at how we can predict it with other systems and things. I mean, we know quite a bit about it, but as far as we know, for instance, there's fast wind comes from coronal holes, and you have slow wind from basically non-coronal holes and things like that. But as far as the actual speed or density of the wind, I'm sure you could probably get measurements by over a long time or somehow. I'm not sure. Yeah.
Probably to be determined.
Yeah, TBD. Yeah.
Are there any implications with understanding the formation of stars? With this magnetic reconnection, we have gravitational forces versus repulsion forces between the electrons.
Yeah, I mean, so, the more we can understand about our sun will definitely shed light, right, into other stars in the galaxy. But so right now I know, for instance, one place that reconnection takes place within the sun or in the corona is it's responsible basically for accelerating X-rays and flare production, solar flares and things like that. And then I think there's papers out where there's reconnection taking place in turbulence as in the solar wind as it comes out. But yeah, I think, understanding how this reconnection and where all it's taking place and how it competes with these different forces. I mean, it's not a force, but this process, how it produces these high energy particles that will then, I think that's something that needs to be further understood, I guess. But I mean, there would definitely be implications in that it'll help us understand, how the solar wind is generated and what makes these different structures and transient events that come off of the sun.
Let's. I don't want to cut anybody off, but we do have to move on. So let's thank again, once again.
Thank you, guys.
If you do have any questions, I'm volunteering you to answer questions offline. So just find him and ask him. Executive decision.
Awesome. Thanks, everyone. Thank you all for coming. What did you think of our two speakers tonight?
Woo!
And a big thanks to Caleb as well for Astronomy in the News. And of course, a big thanks to Blue Star for hosting us. And don't forget to tip your waiters, waitresses, servers. Thank you. I couldn't see the word. Okay, so next up we do have some trivia. So if you, we do have also upcoming events. So next event will be on October 5th. So don't forget, mark your calendars. We generally do the first Wednesday of every month, so we'll see you back then. Anything else? Oh, you went the wrong way. Okay, all right, so if you're sticking around for trivia, we're going to come around with trivia cards. Thank you again for coming out, and yeah, get ready for some trivia.
There we go. Oh, okay. As usual with the trivia, if you need a utensil, geez. A writing utensil. That is a word. Trivia's in teams, everybody, so group up. Oh dear God. Does everybody have, that needs a trivia, want one? Obviously, I forgot to mention, if you're a student, you're not eligible, but you can still write it down. You can still play along. You just can't give it to me and win prizes, which tonight are very, very nice prizes, thanks to Christine. So everybody has a sheet and a writing utensil? I'll take that as a yes. All right, let's. Oh, I'm sorry. I don't know how to do this thing. It's. I feel like I have to hold it all the way out here. Let's start settling in so that we can begin trivia, so that we can have a early-ish night. As always, the rules are simple. The cell phones are not permitted because, well, yeah. And I'm going to ask that you please put down the letter, and only the letter for the answer, for questions 1 through 6. It'll make grading it so much quicker and easier. If you don't put the letter, I'll be sad and mad. Yes, Times New Roman 12 point. Helvetica also, but not Comic Sans. What? Let's go. I forget. Maybe? I would hope so. I want to be encompassing. Everybody should. Yeah. Accessibility. All right, let's get started with our first question. Question 1. The Carrington event, one of the largest recorded geomagnetic storms, occurred in what year? We have A, 1806, B, 1859, C, 1994, D, 2000, or E, 2018. The Carrington event. Anybody need more time? Speak up or forever? No. Question 2.
Question 2. How long can an average magnetic storm power the city of San Antonio? A, 1 minute, B, 1 day, C, 1 month, or D, 1 year? We are assuming the power grid is okay. We're stable in this situation.
Assuming San Antonio was in any other state. Huh?
Is this a piano?
Yeah. I realize now we didn't make an answer key, so when everybody's submitting, I'll run back and make this an answer key. All right. Anybody need more time? Ready to go on? To question 3. Roughly how long does it take for solar wind to reach the Earth? Just in case clarification, from the sun, obviously. It's coming from the sun. That's how the sun's giving it out. A, 1 day, B, 2 days, C, 4 days, D, 8 days, or E, 12 days. How long does it take for the solar wind to reach the Earth?
No. It's just I've always seen it in here. It looked like a piano. Just couldn't tell if it was a piano.
Can have somebody play during the breaks.
Yeah.
Fancy. All right, everybody good? Can move on. Question 4.
Okay, question 4. How many objects in the solar system have been observed to have active plumes or volcanoes? A, 1, B, 5, C, 10, D, 15, or E, 25? And this is just the solar system.
I wonder if we've seen an exoplanet with.
Yeah, I said like just in the solar system, like would we even know outside of the solar system?
Maybe with JWST.
Maybe with JWST.
I don't think.
The future is unknown.
Yes. All right, moving on. Okay, no pushback. Question 5. Before Europa Clipper's upcoming exploration of Europa, several other of NASA's mission have flown by Jupiter and its moons. Which of the following was not a spacecraft mission that acquired data of Jupiter and or its moons? We have A, Galileo, B, Voyager, C, Pioneer, D, Dawn, and E, New Horizons. Which one of these did not take any data of Jupiter and or its moons?
Anybody need more time? Okay.
Good.
Next question. Question 6. On September 26th, what part of the asteroid, I say Didymos, will NASA's DART mission impact? So we have A, its northern hemisphere, B, its moon, C, its largest crater, D, its water deposit, or E, its plume. Once again, on September 26th, what part of the asteroid Didymos will NASA's DART mission impact?
This is a memory recall question. If you don't get it, I know you weren't paying attention. Unless Michael said plasma one too many times and you forgot, so you know. Then that's okay, acceptable if you forget. Huh? All right. Does anybody need me to revisit any of questions 1 through 6? Nope. All right. The bonus. What are the 6 main chemical elements that make up living things?
Once again, another memory recall.
Yep. You can, I'll accept the letters. We'll accept the letters, but tiebreakers would be if you put the full words. So put it on the back. You can put the full words on the back. There's not enough room on the front. Put the full words on the back. Tiebreaker. Thank you.
Okay, very soon we're going to come around and start collecting the slips and the pens. So put your final answers down. Also, be sure you have a team name on there. We need to know what teams are affiliated with who.
I mean, you could have.
I could have tried to use the marker as a microphone. We can go, or you can bring them up. It's up to, what do you think? I usually have them bring them up. We'll come to you this time. But if we gave you a marker, please also give that back because we need those. Thank you.
both got 2 wrong. Question 4.
They couldn't do memory recall, but this one didn't do the hard work.
They both. Did anybody have a spelling error?
Well, this one didn't put it in order to clear. I think we're gonna just this one for now. I don't know. What do you?
I think we should do a tie, but I don't know how we do ties.
Christy, we need you.
This person answered all the questions correctly, but this person didn't recall. They both wrote out all the words. No spelling errors.
Wait, so they had the same number of questions? I would just call for third place. I mean, can we, okay, what are the prizes? First is still first. Third was this over here.
That poster and this little
Can we just give them like a couple more things and call it a tie for third? Or is it just first, second, third? No, there's 4 of them, right?
Yeah.
Yeah.
The prize. We could just hand it to both teams and say, you guys
Split 'em.
decide what you want. Yeah,
All right.
that's what I would do. Because I feel like it's, fair is fair.
All right, everyone. We have our winners, but as usual, we're going to show everybody the answers so you can either feel good or sad. But really, we should all be feeling good because tonight was fun, wasn't it? Yes. All right. So for question 1, which was the question about I really should give myself notes. Oh, the Carrington event. If an incident like the Carrington event occurred in the present day, it could affect mobile phones, internet, and satellite communications. However, this was not a problem in 1859. The answer is B. But, and this is just, just somebody shout out, what existed in 1859 that would be an uh-oh? Thank you. So, that's almost like phones going out. So this was a big deal. All right, question 2 was about how long we could be powered from an event. And the answer was 1 month. A typical magnetic storm contains 10 to the 15 joules, 10 to the 15 joules of power, which can power San Antonio for approximately 1 month. That's a lot of power. And boy, would that have helped us during the winter storm. All right, question 3 is, I wrote that one, I should know, is about how long it takes for the solar wind to get from the sun to here at the Earth. And the answer was C, 4 days. The calculation is 1 AU at 400 kilometers per second average is roughly 4.3 days. 400 kilometers per second is the average solar wind speed. So that's roughly how long it'll take to get here. All right, question 4 was about yes. Unfortunately, I have none. No. Question 4 was how many objects... Oh, no, this one was how many objects in the solar system have been observed to have an active plume or volcano? And the answer is B5. Earth, Triton, Io, Europa, and Enceladus. If you said 1, you probably forgot about Earth. Earth is a planet. Remember, Earth is a planet. Number 3. We went with objects, so it is an object. But all right. Question 5 was about which spacecraft did not go to the Jupiter system at all, and the answer was D, Dawn. It explored 2 asteroids in the asteroid belt, so it didn't make it all the way out there. So pat on the back if you got it, because that one's. Galileo, I mean, you know, the name implies the Galilean moons. It was named that way because it went to Jupiter. Voyager, which is still going all the way out, skimmed by Jupiter on the way and took beautiful photos. Pioneer, it's another old one, but it also took pictures of Jupiter. And then New Horizons, famous for Pluto, but it did do important Jupiter science as well. It's far out, man. I don't know. No, New Horizons. It's still in the Kuiper Belt. I know that much. Still in the Kuiper Belt, yeah. All right, question 6 was about was a memory recall about the dart. What is the dart impacting of an asteroid? What piece of the asteroid is it impacting? And it's impacting its moon. This is really exciting. And honestly, September is a fun month for science because we have DART doing this, and speaking of Juno of Europa, the Juno mission is even gonna pay visit a hello. So Europa's getting some love. So September for the win. All right. The bonus question was about which are the 6 elements important for life. And if you, the way I always remember it, and you know, is you know, it sounds like schnapps, and you really do need schnapps sometimes to get through life. But CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So give yourself a pat on the back if you got them, because that's, yes, round of applause. And that brings us to the end, so that means it's time for winners. Who's ready to win the number 1 prize? Drum roll. Oh, I'm sorry, number 3 prize. Number 3 prize.
Wait, they're first, right? Because they got up.
Yes.
Right up, yeah.
Wait, no, this one. No, because they forgot. So for the 3rd place, slightly unprecedented. I think it's happened before, but we had a pretty good tie. We couldn't break the tie. So what we're going to do is we're going to bring both people up here, and then you all decide how you're going to split the multiple things for winning civilly. We have in 3rd place Scott T. and Team 1. Hello? Come on up, and round of applause. And throw in that thing there, extra. Yes.
What do you think?
Oh wait, both of you can take a Europa sticker. You know, that way both of you can get one. Everybody deserves a Europa sticker. That one's too. Okay. All right. In our 2nd place spot, we have. Oh, I like this team name. I'll give you a hint. I'm from Miami. The winner's Florida. Oh God. Okay. Round of applause. Christine. Mars is 2 and Europa 1.
Cool. Thank you.
Yes. All right, the grand prize that Europa posters included. The grand prize, you're getting a whole lot of stuff here, so get excited. J&M. Woo! Come on up. Look at this, stickers galore. Look at this beautiful bag. It's an ESA bag. ESA is the European Space Agency, all of their missions. And this, sorry it's crumpled. I hope you can flatten,
I
you know.
can flatten.
Okay.
Thank you. This is a blast. Thank you.
Yay. Woo.
Way cool.
All right, round of applause for all our winners. And if you didn't win, applause yourself, because everybody got at least one right. So, you know, we're all winners. Just some more than others. Thank you, everyone, for coming. And of course, thank you to the speakers, Dr. Christine Ray and Dr. Michael Starkey.
Thank you again to Blue Star and to your servers. Thanks, everyone. And we'll see you all back here in October. So thanks again. Feel free to hang out. Come talk to the speakers. And we'll see you all next month.
And merchandise. Come get merchandise, keychains, fun stuff, stickers.
Cheers.